Hello there. Welcome to College Algebra, section 2.7. My name is Gregory Carlson. In this section, in the previous section, we learned about parent functions, and we learned a little bit about how to graph piecewise functions, which can be tricky at first. It takes some practice. Now we're going to look at translations and how we can move these parent functions around. So we're going to use the example of x squared. And you should know what the parent graph of y equals x squared looks like. It's on that parent sheet, which was page 25. It basically looks like a u. So x squared looks like a u. Let's talk about how to transform it. Here is the standard graph. This is actually called the vertex form of the graph of a parabola, because you can see the vertex, which would be h comma k. And I know this is a little blurry, but hopefully you can read it on your page. So we're going to see how can we move this function around. So check it out. This red one right here is y equals x squared, or f of x equals x squared. And you'll see that if we subtract 2 inside the argument, inside these parentheses, it shifts it to the positive 2 spaces. And so that's just something to remember. If we add or subtract inside, it moves us left or right, and it moves us in the opposite direction. So x minus 2 means we move 2 to the positive. This should make sense because if you plug in 2 right here, you get 2 minus 2, which is 0, and 0 means we're on the x-axis. So 2 minus 2 is 0, 0 squared is 0, so we're on the axis right there. The good news is that all of this works the same for every parent graph most of the time. So check it out. If we add 2, it takes us from our parent graph and moves us 2 to the negative. Here are some more transformations. If we add a number on the outside of the square, if we add it on the outside, that means it's going to bump us up or down. And so if we add, it bumps us up 2 spaces. If we subtract, it moves us down 2 spaces. So look at the difference between these. Here, I added or subtracted inside the parentheses, and so it moved me left or right, and it moves me in the opposite direction of what we added or subtracted. When I added or subtracted on the outside, it moved us up or down, but in the correct direction. Plus 2 means we went plus 2. Minus 2, we went minus 2. You'll be happy to know that these transformations, the ones we just looked at, pretty much are the same across all parent graphs. So you'll notice that if we add on the outside of an absolute value, it'll bump us up 3 or down 4. If we subtract or add inside the absolute value, that moves us left or right, but it moves us in the opposite direction. And so if it's minus 2, then that means we go 2 to the positive direction, or 2 to the right. If it's plus 1, then that means we move 1 to the negative direction, 1 to the left. If you multiply a function by a number, if that number is big, it means that the graph is getting bigger faster, which means that the graph gets skinnier. If you multiply by a fraction, then that means it takes the graph longer to get big, which makes the graph wider. So that's another thing to memorize. If you multiply by a number, it vertically stretches it, meaning it makes it narrower. If you multiply by a fraction, it compresses it horizontally. Same with the horizontal compression. Well, these are kind of connected, these two. Finally, if you throw a negative sign on it, it flips it over the x-axis. So your graph reflects across the x-axis, or you can think of it as just flipping across the x-axis. So let's look at an example of everything I just described. We're going to do all of these things to the graph y equals x to the 3. We're going to be able to graph all of these because we know that the graph is dominated by this x to the 3rd term. And so that's its parent. Basically, we're just going to be taking that parent and stretching it and pulling it and shifting it around, that parent graph. So let's start with x to the 3, the regular parent graph. That's on page 25 of the notes. We have a 0.1 and a 0.11, because if you plug in a 1, you get 1 times 1 times 1, which is 1. Same with negative 1. Negative times negative times negative is negative 1. If you plug in 2, you get 8, because 2 times 2 times 2 is 8, and negative 2 times negative 2 times negative 2 is negative 8. So there's our cubic graph right there, just our regular old cubic function. That's the parent graph. Okay, so that's easy enough. And that should be a little better curved through their curves like that. All right, so let's see. If it's x plus 2, how would that shift it? The entire graph is going to be the same, except now it's just going to be shifted. It's inside the cube, so that means it's going to be left or right. And remember, we move in the opposite direction, so our entire graph gets shifted 2 spaces to the left. So instead of having a point there at the origin, we move it 2 to the left. From here, it's up 1 over 1 and down 1 over 1. And then it's still over 2 up 8 over 2 down 8. You have to have good eyesight to see these tiny graphs. So there you go. You can see that our cubic function is the same as this cubic function. It's just been shifted over to the left 2 spaces. So let's do this one. Y equals x minus 5 to the third. Why don't you pause the video here, see if you can get it yourself. Did you get it? I hope you paused it and got the answer. X minus 5 is inside the parentheses, so we're moving left or right, and we move in the opposite direction, so we move to the positive 5 spaces. So there's our kind of starting point right there. Everything else is the same. Up 1, over 1, down 1, down 1, over 2, up 8, over 2, down 8. So you see that these transformations are easy if you know which way to shift the graph. So look at the difference between these two and make sure that they make sense to you. How about, again, we're building all of this off of our parent graph. So what would y equals 5x to the 3 look like? Well, as I said earlier, when you multiply by a number, that makes the graph get steeper. It makes it more narrow because the graph is getting bigger faster. So in fact, if you plug in a 1 here, we see that 0, 0 is going to be the same, so that's good, because plug in a 0 and you're going to get y equals 0. However, this time if we plug in a 1 for x, we get 1 times 1 times 1, which is 1, times 5 is going to be 5. So it's over 1 up 5. You see how it's getting narrower? Over 1 down 5. In fact, over 2, it's going to be over 2 times 2 times 2 is 8. 8 times 5 is 40. So it's going to be over 2 up 40, which is way off our graph, and over 2 down 40. So we can't even put those points on our graph, so we'll just stop there. And so you can see, hopefully, this graph is narrower than this graph because we multiplied it by the 5. Let's do these last two, and then we'll finish this part. Notice that this time I have plus 2 and minus 6 on the outside of the cube. That means we're going to go up and down. The nice thing about adding or subtracting in this way is that it goes in the direction we expect. We're adding 2 to the y value, so we're going to be up 2. Everything else on the graph is the same. Over 1 up 1, over 1 down 1, over 2 up 8, over 2 down. And by the way, when I say over 2, I'm going from the origin spot here. Over 2 this way, over 2 this way. So over 2 down 8, 1, 2, 3, 4, 5, 6, 7, 8. That's just the way you graph a cube. You start with that. There you go. You start with that 0, 0 point, and then it's over 1, up 1, and then starting there again, over 1, down 1. Starting at the origin again, over 2, up 8, over 2, down 8. Then it would be over 3, up 27, because 3 times 3 times 3 is 27. So as you can see, the plus 2 on the outside just shifted the graph up 2. If we add plus 2 inside, it moves us to the left 2. So make sure you keep those straight in your mind. Also remember that if you don't remember how to do this, just plug in points for x. Just plug in points for x, connect the dots, and you're going to get the right answer. You can always do that. X to the 3 minus 6. The minus 6 is on the outside, so that bumps us down 6 spaces. Over 1, up 1, over 1, down 1. We're going to be off the graph in that direction. So let's go over 2, up 8, 4, 5, 6, 7, 8. There we go. And that'll be good enough. So you can see that by subtracting 6, we bumped the entire graph down 6 spaces. So you can see that these shifts are pretty easy. They're either going to go left, right, up, or down. They're either going to get skinnier or they're going to get wider. but these essential shifts are very much the same for absolute value, or x squared, or x to the third, the square root function, x to the fourth, you name it. So in the next part 2, we'll do a little bit more practice. I'll see you there.